Welcome to the presentation of our work MASTIFF, a structure-aware minimum spanning tree and forest. Our group in Queen's University Belfast consists of Professor Hans Vandierendonck, Professor Peter Kilpatrick, and me, Mohsen Koohi. Minimum spanning tree of a weighted and undirected graph is a tree over all vertices and with minimum sum of weights. Minimum spanning forest of a weighted undirected graph is a set of trees of different connected components of the graph. Minimum spanning forest has several usages in different fields of technology, science, and humanities. Boruvka's algorithm is a parallel algorithm for identifying a minimum spanning forest. It consists of a number of iterations. In each iteration, the lightest edges of vertices are identified. These edges are added to the minimum spanning forest, and the vertices that are connected by these edges are merged into a vertex. The new graph is used in the next iteration. As an example, we consider the execution of Boruvka's algorithm for this graph. After the first iteration, we have vertices 7 and 8 that are connected by an edge of weight 1. And similarly, we have vertices in two other components. After the first iteration, the connected components by edges of the minimum spanning forest are merged, and we have three vertices A and B and C that are connected by two edges of weight 3 and 2. This new graph is used in the next iteration, and the process of finding lightest edges and contracting the graph is continued until we have only one vertex for each connected component of the main graph. While Boruvka's algorithm benefits from a high level of parallelism, our evaluation shows that 56 to 81% of execution time is passed in contracting graph, which includes merging and relabeling vertices and neighbor lists. Moreover, power law graphs have a high degree of connectivity, and the very large degree of connected hop vertices in these graphs results in quick formation of a component containing a large percentage of the vertices and edges. Our evaluation shows that after 3 to 6 iterations, a giant component is formed that contains more than 50% of the vertices. The two main problems in processing Skewed-Degree graphs using the Boruvka's algorithm are high overhead of contracting graph and formation of a giant component that requires a large percentage of the execution time. On the other hand, when we select lightest edges between V connected vertices, at most V-1 unique edges can be selected, and at least one edge is selected twice. So it's more efficient to process V-1 vertices. So the best candidate to be skipped in processing is the giant component. We introduced the MASTIFF algorithm that tracks the joint component and exempts it from processing. And as we don't process the joint component in different iterations, we don't need to contract the graph after each iteration. As an example, in this graph, the vertex with max degree is initially exempted from processing. After first iteration, 5 other vertices that are shown with green backgrounds has been attached to the joint component. These vertices are exempted from processing in the next iteration. We evaluate MASTIFF in comparison to implementations of Boruvka's algorithm in GBBS and Galva, and for graphs of up to 124 billion edges, and in two CPU architectures of up to 128 cores. The evaluation shows that MASTIFF is 3.3 up to 5.9 times faster than previous works. Conclusion: finding minimum spanning forest of Skewed-Degree graphs using Boruvka's algorithm requires the contracting graph which has a high overhead, and also a joint component is shaped in initial iterations of Boruvka's algorithm. We introduced the MASTIFF algorithm that tracks the largest components and exempts them from processing. In this way, MASTIFF doesn't contract the graph and provides better performance. Thank you, and further discussions are available on our website blogs.qb.ac.uk/graph processing. Thank you.